is Frank Baudin, and I want to present you today EgressService+VRF within a Red Hat OpenShift context. Before diving into the technical content, a quick disclaimer. You can pause and take the time to read it. The key takeaway of this disclaimer are: number one, I'm a Red Hat employee, but those materials do not represent any official statement or position of Red Hat. And second one, you should not use any of this content in a production or mission critical context. The agenda for the presentation. The first use case of EgressIP+VRF is static route update. The second use case is routes overlapping CIDRs. And the wrong use case, when you should not use EgressIP+VRF, Kubernetes service overlapping CIDRs, followed by a demonstration. If you want to get a configuration example or details on the traffic steering, please have a look at the previous presentation I've done on MetalLB 201, Advanced Traffic Steering, 16 minutes offset on the same YouTube channel. So, first use case, routes. Let's have a look at Kubernetes and OpenShift cluster, where you have a first network with OVN Kubernetes, where the Geneva overlay is hosted. That's a cluster network, and where the API, the cluster API, are exposed. And then you have a second network where the services are exposed. And let's say this VLAN is connected to a VRF, a network VRF, where remote cluster can connect back and forth to the cluster. So either for this cluster to exit, either those clusters to access to a service. So let's say the red network is kind of the management network, and then you have a second VRF which is used for operational traffic, like site-to-site state machine configuration, like in a 5G network, the signaling peer-to-peer between 5G core sites networks. So these two networks should not mix traffic, because you don't want to mix management and signaling. You never want to do that. So this is why you have two different VLANs here and two different VRF. So in order to configure your OpenShift cluster to segregate traffic, what you do is you have static routes per VLAN. And when a packet exits a pod on this cluster, depending on the destination route, it's going to exit on VLAN 10 and 20. So it's working just fine from a traffic segregation perspective, except that every time someone add, remove, change the configuration of a remote site, you need to update your static routes on your OpenShift cluster. So this can be done via DHCP or by pushing a new NNCP configuration in your OpenShift cluster, but this requires automation and a human to push the button, trigger the update, because that's kind of a you need to have someone taking the responsibility of, okay, I acknowledge that there is the remote change, or you need to have an overall orchestration of all of your sites. All possible, can be automated more or less, but it requires an update of your cluster configuration. So EgressIP is going to resolve that problem. The other way to resolve this problem is to use BGP instead of static routes, and that would be my recommendation as soon as you have a BGP capable network, and that should be the case. But there is another use case for EgressIP+VRF. So yeah, every time a remote site configuration change, one site is added, removed, you need to update your static routes. And I would recommend to use BGP instead if this is your only problem. Because the other problem that you may have is on these two network VRF to have the same colliding CIDR, overlapping CIDR. So you have the same route in this example on the two VLANs. So without EgressIP+VRF, it simply does not work. So this is where this feature is mandatory. So yeah, EgressService+VRF is solving both the overlapping CIDR and the static routes update by pushing one default route per VRF and ensuring that on the Linux host you have a strong isolation between the two VRFs. So all of the packets that should go through VLAN 10 and VRF 20 go to this VLAN and not to that VLAN. So I'm going to deep dive on how it's working on the OpenShift node. But so one thing I want to add is overlapping routes CIDR with BGP is also possible with EgressIP plus VRF, but instead of using static routes with EgressIP plus VRF, you use BGP with FRR Kubernetes. So this is something which is supported and documented. I will not deep dive into this configuration today, but just to say that if you have overlapping remote site CIDR with static routes or with BGP routes, you need to use EgressIP plus VRF as of today. And this is working for both static and dynamic routes. And by the way, you can mix dynamic routes on VRF10 and static routes on VRF20. No problem, it's all possible. And in my demonstration, I've got a mix of this configuration. But this is not something I'm going to deep dive today on. So let's have a look at the traffic steering on a node. So we have our node with a default VRF. Let's say that's VLAN 170. Like any telco setup, there is never one interface per network, per VLAN, but always two network ports connected to two different top-of-rack switch. In case of the one switch fails, you still have connectivity with the other one. That's why you use a bond. So let's say pod 3 wants to connect to the default OVNK or API network. So this is how it's working. Pod 3 is going through OVNK and going to the kernel stack because we are using OVNK local gateway mode. This is the only mode which is supported with MetalLB and for telco use cases using MetalLB. So this is a mode that you're using, so all of the packets are getting through the kernel stack before entering the OVN stack. So now let's say I've got another VLAN. This is VRF20 mapped on VLAN 162. And pod 2, you attach an egress service, so a service and an egress service with the specification of VRF20 in pod 2. And because you put VRF20 spec in the pod 2 egress service object, all of the packet getting in and out the node coming from that pod, you're going to exit via VLAN 20. Pod 2 talking to pod 1 or to a pod on another node will not go through that VLAN. They will stay within the OVN Kubernetes overlay, the Geneve overlay. And this is something that I explained in my MetalLB 201 Advanced Traffic Steering presentation. So this traffic path is for all of the traffic destinated or originated to the outside of the cluster. So the pod not talking to another pod is going to exit via VRF20. So that pod will not be able to exit via the default VRF or any other VRF. And you can create another egress service. So this time with a spec VRF10 and pod 1. All of the packets getting in and out pod 1 at the destination of outside of the cluster. The cluster network is going to be forced via VRF10. And this is how you achieve traffic segregation between pod 1, pod 2 for external traffic. All of the traffic will go directly to the pods, to the pod with the egress service with the spec VRF10. Now, let's have a look at something that you could misunderstand. So, overlapping CIDR for services. So let's say, as before, I've got my two pods, VRF10, VRF20, pod 1, pod 2, life is good, and then but the problem is the service that I've created is on the same CIDR, .1, .2. So nothing in the API as of today, I'm talking about Red Hat OpenShift 4.17 as of today, and nothing is preventing you to push that configuration on the cluster. But it's not going to work. It's not working. So you will be able to push a configuration that will not do what you expect. So just don't do it. To summarize, EgressService+VRF permit to simplify static routes configuration by having one default route per VRF per VLAN. It allows overlapping CIDR for node routes. The routes can be static or BGP. Both work, and you can have a mix of static and BGP you choose per VLAN per VRF if you want to go static or BGP. And EgressService+VRF do not permit to expose service with overlapping CIDR onto different VRF. It doesn't work. There is no protection against it, so just be aware. Don't do it. You have been warned. So, time for the demonstration now. All right, so this is my lab, this is my setup. So I've got my OpenShift cluster with my DC gateway, which is a Linux machine running FRR. On which I've got configured 2 VRF. On VRF 10, I've got a remote machine which is named router 10 hosting this IP address, and I've got on VRF 20 this router 20 machine hosting the same IP address. Okay, so those IP addresses are configured on the loopback interface, and they have some other local interfaces. And on my OVN cluster, all of the worker nodes have a default VRF, which is connected to VLAN 161, and there is a VRF 20 that is connected to VLAN 162. So basically, the VRF 10 is connected to the default VRF of this OpenShift cluster. And why that? Because I don't have a clash between this cluster network CIDR routes and the VLAN 10 CIDR routes. So if I had clash, I would have created another VRF, but for this demonstration, it's not necessary. So we're going to create in the default VRF connected to VLAN 161 a service, and the service IP is going to be 10.200.10. And so it's going to run on worker 0 and on worker 3, so HTTP 3, an HTTP server attached to VRF 20 via a service and an egress service with a specification of VRF 20. So what's important is this 10.220 versus the 10.210, and both are going to be, and router 10 is going to connect to HTTP 0 via VLAN 161. Router 20 is going to connect to HTTP 320 via VLAN 162 with traffic segregation. Everything is going to work just fine. And then the second part of the demonstration is same setup, but this time we use we will update the service IP to 10.200.20.180. So it's going to be part of the same CIDR of the service on VRF 20, and this is not going to work, and I'm going to show you why. Okay, let's go on the lab. So let's first check the IP address configuration of one of the worker nodes. So let's have a look at worker 0 and its default VRF. As you can see, you have multiple routes, and the interesting one is 10.220.00/24. That's going to come from router 10, which has been learned via BGP and going via ENS for 161, VLAN 161. And let's have a look at the VRF 20 configuration. And as you can see, I only have one default route and on VLAN 162, and this is via this default route that we are going to reach the same 10.20.00.0/24, but this time it's going to be held by router 20. Let's connect to the DC gateway and have a look at the VRF 10 IP addresses. So VRF 10, on the VRF 10 I've got this IP address, so this network announced via router 10, and on VRF 20 it's announced via router 20. Okay, so let's create so we are going to create a pod and a service, HTTP 0 and a service for 8080, and that's going to be the IP address. Okay. So this is on the default VRF. Okay, they are created. We're going to create a service and an egress service on sorry, it's not very readable, VRF20. So we're going to create a pod, and the service is going to be this one, and there is an egress service attached to it, and it's coming from VLAN 161. Okay, 162, sorry. So both are created. So let's have a look at the pods. So I've got two pods, and let's have a look at the logs. Okay, log on HTTP 0 here, logs on HTTP 320, so VRF10, VRF20. Let's have a look at the services. So HTTP, on the default VRF, I've got 10.200.10.80, and this one is 20, that's on VRF20. HTTP 20 is exposed by this one, HTTP by this one on the top. All right, so because the pods have started, so we can recheck. So on VRF20, we see that the service is announced via MetalLB, that's expected on this VLAN. On VRF10, it's the other one, this one, which is announced. Okay. So let's have a quick look at the configuration of the router 10, and just to show that router 10 has this IP address on its loopback, and router 20 has the same. Okay, same IP address here and here on the same machine. This machine, router 20, connected to this one on VLAN 20, and router 10 connected to the DC gateway on VLAN on VRF10. Okay, so so what we do is, from router 10 we're going to curl our service on VRF10. So we're going to show a log here. Okay, so the source IP address is 10.20.00.1, and is where the traffic went through VRF10. And then we are going to do the same, but this time from router 20. We target this .20 service with the same source IP, and this time, okay, you see that we have been reaching this other VRF, so it's working just fine. And for the sake of traffic segregation, if we do a quick check, so from router 10, we try to reach this VRF20 service, and it's not working because it's not in the same VRF. There is no traffic connectivity, so it's working as expected. So now let's try to do something that's not going to work. So okay, by exposing two services with the same CIDR on the two VRF. So it's going to be accepted but not working. So let's get the BGP advertisement on the system. So as you can see, on VLAN 161 we have the IP address pool 161, and on VLAN 162 we have IP address pool 162. Let's change that. So what we're going to do is we're going to change this this one to use the same IP address pool as the 162. Okay, so let's do that, and let's check. So now we have the two BGP advertisement using the same IP address pool, and okay, and let's okay, and now let's update. So we're going to update the service HTTP to use the wrong IP address, okay, and to use the IP address pool 162. So, okay. So let's check the service. So same CIDR, 180, 180. So let's have a check at our DC gateway, the routes, and let's check on the VRF10 and what we can see. And okay, we see that on VRF10, we see the two services. That one was kind of expected, but that one is coming from the VRF20. So basically, we are exposing the services of two different VRF on one VRF. It's just not working. So there is no protection against it. So just don't do it. The key takeaway is really the VRF, the EgressService+VRF are used to have overlapping CIDR for node routes, but absolutely not services. That's really the key takeaway. And with that, I'd like to thank you. Have a great end of day.